Hi everyone. Let's take a short break from post-processing effects. In this tutorial, I'll be creating a dynamic ornament that at one stage resembles a magical portal and at another something like a fiery eye. Essentially, it's another demonstration of how we can use iterations and simple functions to achieve quite interesting transformations that can be further configured and combined in new ways. So, let's get started. And as usual, let's start by creating a new scene in the Godot editor. Then we'll add a color rect to the scene, set the parameters, create a shader material, just the usual stuff. So I'm right-clicking on the scenes folder, creating a new scene. It would be user interface, and let's call it ornament, for instance. Okay, and I'm adding a new child node that would be of the color rect type, and in the inspector let's set the color to black and the layout to our usual full HD dimensions, 1920 by 1080. Okay, and I'm scrolling down to the materials section where I'll set a new shader material, click it, and add a new shader, which is called ornament.gdshader. Type is shader, mode canvas item, and I'll just put it to the shaders folder and create, and click again to open it in the shader editor. Let's expand this panel, and let's get rid of everything we won't need. So only the fragment function remains. Deleting vertex, deleting light, and saving. Let's start coding. As is common with similar effects, we'll control their properties using plenty of uniform parameters, which we can then adjust in the inspector. This time, I'll be adding them gradually, so it's clearer what we need each one for. Okay, let's start with the resolution parameter, which, as you may know from previous tutorials, we use to recalculate the aspect ratio so that we achieve the same effect regardless of the size of the element to which our shader is applied. Uniform, vec2, resolution, and the initial value should be vec2 1920 1080, the same as the dimensions of our color rect full HD. Okay, and we'll use this parameter right away in the fragment function. As we saw at the beginning of the video, we are creating a symmetrical effect, so we'll need to move the coordinate origin to the center and then recalculate the aspect ratio in the usual way. So let's do it here. Vec2 UV is UV minus 0.5, moving the origin of the coordinates to the center, and there should be minus, not equals. And the aspect ratio UVX is multiplied by resolution X divided by resolution Y. Okay, let's move on. The effect will be computed in a loop, meaning in iterations. So I'll add the number of iterations as another uniform parameter. Uniform float iterations with a hint range, and let's start with 20 iterations. So the range should go from 1 to, let's say, 50, and the step is of course 1. Okay, and we'll set up the loop where the calculation will take place. I'll also define the result variable, which will be computing and modifying within the loop. So float, caps lock, the most useless key on the keyboard. Result is 0 and the loop for float I from 0 to the number of iterations, and I plus plus, okay, and the block. All right, and now we'll do something new. You might remember from previous videos that we usually calculated the result value in some way and then used it as a grayscale shade in the final effect. Sometimes we also colored the result by multiplying it with an RGB color, but that was usually the end of it. This time we'll do it differently. I'll use the smooth step function to achieve smoother color transitions. So first I'll add a uniform parameter that will allow us to control this color gradient. I'll call it inv_color because in the end it will represent the inverse color of the one we want to achieve. I'll demonstrate that later in practice. Okay, so let's get back to the uniform parameter section and uniform vec3 inv_color with the hint source color and the initial value vec3. Let's do this 0.1, 0.2, 0.3. Okay, as you know, the source color hint means that the Godot will add color picker into the inspector at the shader parameters, and we can see it right here. This is exactly the color we won't see because it is the inverse color, but as I said, we'll get to that. And now I can insert the mentioned color calculation and its display at the end of the fragment function. Let's do it here. So vec3 color, and as I said, it would be a smooth step function on vec3 0 0 vector black color. Now our inverse color inv color in the vec3 result as the value. All right, since we are applying the smooth step function on vector 3, all its parameters must be vector 3 as well. That's why we are using it here and here. All right, and finally, let's assign to the output, which is the internal color variable, a vector 4 that consists of color and 1 for the alpha channel. All right, for now, we only see black everywhere because the value of the result variable is remains 0, which equals to the value of the left edge of this function, which is vector 3 0 black color. So it's time to use some actual calculation. Its basic form will involve adding the distance of the current pixel from the origin, that is, from the center. So it's simply the function length. Let's do it here. Result equals result plus length of uv. Semicolon. Okay, and let's show everything. We can finally see something, a small dot here in the middle. So when I change the value of the iterations parameter in the inspector, we can see this dot growing or shrinking, revealing layers in different shades of orange. Let's get back to 20 iterations. So this happens because with more iterations, the result exceeds the value of 1, which corresponds to white. However, one dot doesn't help us much because we need something periodic. That's where trigonometric functions are practical. So let's try adding the cosine function. I will just wrap the length in the cosine and the end bracket here. Okay, it seems we can't see anything now. That's understandable because the cosine starts at 1, which is white, and then slowly decreases. Let's demonstrate that in the Desmos app. So I'm opening Chrome and Desmos is opened here, desmos.com. And when I enter the formula cosine x, right here, cosine x, we can see the graph of the cosine function, but we have to remember that in a shader we work with UV coordinates, meaning the range from 0 to 1. In addition, we've moved the coordinates origin to the center, so now the interval is negative 0.5 to 0.5. Okay, so when I click here on the graph settings and set the interval for the x-axis, as I said, from negative 0.5 to 0.5, and here 0.5, and close it, we can see, we'll see that the result is indeed very close to 1. This is 1, and this is this particular part of the cosine function graph. So we need to change the zoom factor. Let's go back to Godot and add a uniform parameter for it. Okay, scrolling up to the parameters section and uniform float zoom with a hint range, and let's start at equals 20. Okay, and the interval should be from 1 to, for instance, 100, and the step 0.1. That's okay. All right, and now we need to use that zoom in the code, which will be pretty simple. Let's just add this multiplication. UV is multiplied by zoom factor. Okay. Now we can see something more interesting, but we are only at the beginning, still very far from the final ornamental result. The image is especially too circular, so we'll introduce some deformation. First, I'll define a deform variable inside the cycle, like this. Vec2 deform is vec2, and let's use trigonometric functions again. Cosine of the I value and sine of I. All right, and now I'll use it in the result calculation. So here UV would be multiplied by the deform vector. Wait for it. Okay, so it's starting to look a bit wavier. Notice that when I lower the iterations to a value of something like 4, we can already see a hint of the desired fiery color. So let's get back to 20 again. However, since we are using addition right here, a higher number of iterations causes the result to become overexposed. So I'll normalize this value by dividing it by the total number of iterations. Result is divided by iterations. Okay, very well, much better now. Still, we haven't achieved a particularly ornamental shape yet, because the cosine function's values oscillate between negative and positive numbers. So let's try improving it using the absolute value. Let's get back here and use abs and bracket. Wait. Okay, we are getting close to the final effect. To emphasize the less bright areas, like here or here, we'll subtract a certain constant from the result value. I'll define it as a uniform parameter and call it contrast. So uniform float contrast and the range, and let's start at 0.6, for instance, and it would go from 0 to 1 with the step 0.01. And now, as I said, let's subtract it from here. Minus contrast. Okay, very well. Let's see what happens if I increase the contrast or decrease it. Yeah, very nice. Let's get back to the default value of 0.6. Okay, but one important detail is missing. Yes, the effect is static and doesn't move. So I'll add a parameter for animation speed. Uniform float speed and a hint range, and let's start at speed equal to 1, and it should go from 0 to, for instance, 10, again with the step 0.01. 0, 1. And to use it, I'll define a variable called time. And since the speed would still be too high, I'll divide the result by 10, like this. So let's put it here. Float time is time internal times speed times 0.1, which is the same as dividing by 10. Okay, and now I'll add this variable to the calculation. After a few experiments, I found that the best result comes when I add time to the cosine function's argument and subtract it from the sine function's argument, which creates more interesting interference patterns. So let's find the deform definition here, and as I said, adding time here and subtracting from this. Okay. Looks pretty fine, and I would say our ornament is complete. And now, as I mentioned at the beginning, we can demonstrate that the inv color value is indeed the inverse of what we see in the end. For example, if I click here in the inspector and set the red component to 0 and everything else to the maximum, we can see that the result is indeed red, because that's the one we didn't see in this RGB format. Similarly, I can demonstrate the green or blue colors. So let's put green to 0 and red to maximum. This is green or blue. Yeah, I would say it's pretty obvious. So let's get back to our fiery color. One last thing. If you don't like this bright spot in the center, we can easily filter it out using another smooth step function, which will multiply with the result. And since we know that the size of the spot changes with the zoom factor, bigger, smaller, changes with the with the zoom factor, we'll need to include it in the calculation like this. So here we have the color, and let's alter it like this. Color is multiplied by a smooth step. Yeah, smooth step. And from 0 to 20 divided by zoom. This is the zoom factor I mentioned, which should be included in the calculation, and not only here, but also in the value. So length of UV divided by zoom, and let's try it out. Okay, I guess maybe it's too big, so let's multiply zoom by 2. Yeah, now it's better. And if I zoom in, zoom out, the center is still darkened, so I guess it works fine. And of course, if we want to keep the option to dynamically enable or disable this filter, we can add one more uniform parameter, which will appear in the inspector as a checkbox. So I add it here, uniform bool for boolean, and let's call it hide center, and it should start with true. Okay, and then now we can use it in the code. So basically we need to do this. If hide center, so it's true, we do this calculation. Okay. Yes, and now when I go to the inspector and uncheck it, we have the bright spot back, and let's get rid of it again. Okay, and that's it. We are completely done. Although I just thought of one more improvement. It might happen that we really like a certain phase of this animation and want to use it in the game. Therefore, it would be more convenient to manually set the value of the time parameter, which controls the entire animation. So let's add time as a uniform parameter. Uniform float time, and let's give it some hint range, and it starts at 0. Okay, and let's say it would go from 0 to 100 with the step point 01. And now, of course, we have to comment out this declaration. Okay, so it is back, and we can now move the slider in the inspector and look for a suitable ornament. Okay, so where is it? Here. Let's move it. All right, I think maybe it's a bit too sensitive. So let's try entering some values directly, like 1, 2, yeah, looks pretty nice. 3, 4, what about 4.1? Yeah, this is pretty impressive. And so let's remember the value 4.1, and I'll add a short GDScript to the scene to create slight fluctuations. So selecting the root node and clicking this icon, which adds a GDScript. Let's click create, and now it's here, and we'll need reference to our color act. I just dragged the node while holding the control key, so it created this already declaration. And let's create a variable for the value, which is, as we remember, 4.1. And since it's supposed to be slightly changing over time, we should calculate the time. So var elapsed time starts at 0. Okay, and now we need the function process, which is called on every frame. And to change the parameter, we'll do this. Color rect material property and the function set shader parameter. And as we know, the value, the name is time, and the value we called value. Okay, and of course the value should change over time. So first I'll do this. Elapsed time is increased by the delta value. And let's try, for instance, adding the result of a sine function plus sine of elapsed time. And I guess it would be too big of a change. So let's multiply that by 0.1. Okay, and I'll try it out, starting the scene. Yeah, looks nice. Maybe it's too fast, so let's get out of that and multiply the elapsed time by 0.1. Trying again. Yeah, I think this could be quite usable. And I guess this is definitely an idea for further experimentation. In the end, we could find the most fitting combination for our game. For example, if we wanted to highlight that the hero is going through a dream or a hallucination. But I won't do that in this video, as it would make it too long. Let's exit the scene. Okay, did I say we are completely done? Well, not quite. There is one more thing I regularly forget about, and people often ask about it in the comments. So what is it? It might be useful to display this ornament on a transparent background, which we can achieve with a simple modification of the last line in the fragment function. But first, I'll define a uniform parameter called alpha threshold, which will control this calculation. Uniform float alpha alpha threshold with a hint range and the initial value equal to 0, and it goes from 0 to 1 with the step point 01. And now for the mentioned code adjustment, I'll get the average color value of the pixel of this vector and compare it with the alpha threshold value. So let's do it here. Float AVG for average is the arithmetic mean, so color R plus color G plus color dot B divided by 3, of course. Okay, and now in the last line, we use this formula. If AVG is less than alpha threshold, use 0, transparent, otherwise use 1 for opaque. Okay, and now, where is my material? Here? No. Let's select again. Alpha threshold, I'm changing it, and now I guess this is exactly what we want if we need the transparent background, where we can experiment with the other values and get some modifications of the pattern. Okay, and I guess we are completely done. Many thanks for watching and for every like, subscribe or both. Since it takes only a relatively small number of iterations to achieve a usable result, this shader should be fast enough even on less powerful GPUs. In any case, we've created quite an interesting addition to our collection of shaders for Godot 4, and of course, I'll include it in the Godot shader pack, along with the sample GDScript. So, once again, thank you for watching, have a great day, good luck with your projects, and I'll see you in the next video.